Okay, guys, so we're looking at these questions here, and the question that's been asked of us is looking at P and looking at Q, using 7 bits for the mantissa with 5 bits for the exponent, can we figure out whether the number is normalized or not? And essentially, we have two types of numbers. The number will either be positive, or it's going to be negative. So it's going to be a positive number or a negative number. And the way we hold that in the mantissa will be different. Now, how is it different on the mantissa if it's positive and negative? So the answer I've just got was that it's 1 in the front, so it's 1 point something if it's negative, and it's 0.1 something if it's positive. The bit we've missed out here is what's the number here going to be? Could it be 0 or 1?
Has to be a 0.
Has to be a 0. There we go. Now, with that information, we can now look a bit more closely at these two values. I'm not even needing to convert it. The mantissa, is that the first 7 bits or the second 7 bits on this number?
First 7.
So those 1, 2, 3, 4, 5, 6. So those 7 numbers there. Is it 1.0 something?
Yes.
Indicating it is a what? It is a normalized, and in particular it's a normalized negative number. And we do the same with Q if I go across. And what do we see? It's 1, 1 at the beginning, indicating that it's 1.1. So what kind of a number is it? It's not normalized because it has to fit one of these, either 1.0 if it's negative or 0.1 if it's positive. 1.1, not allowed. So it means it's not normalized. And so if the point is here between the front two, what you'd need to do is you'd move it up there. If I move it to the right, am I making the mantissa bigger or smaller? Bigger. I am making it bigger. Now, the way to remember that, of course, and I've talked about this before, if you had, say, 17.4, if I moved the point from here to here, making it 174, have I made it a bigger or smaller number? Bigger. If the mantissas become bigger, what will have to happen to the exponent? Smaller. And so you'd have to so if you move the point there to make it normalized, I'd have to add in a 0 on this side, and then with exponent, because I've moved it 1 to the right, because I made the mantissa bigger, I'd have to make the exponent, I have to take away 1 from the exponent. Okay, but to answer the question, P is the normalized number, and we recognize it's normalized because it starts with 1.0 in the mantissa. Q is not normalized because it starts with 1.1. To be fair, it has not asked us to normalize it, so, okay? Okay, quick look at this question. It's saying a binary number could be using a 7-bit mantissa and a 5-bit exponent again, both in 2's complement, meaning they can be negative as well as positive. The binary R is not normalized. Using the knowledge we've just talked about, how can we tell this is not normalized?
It's not 0.1 something.
There we go. So the point should be here, should it not?
Yeah.
So we're going to have to move it up. Will that make the mantissa bigger or smaller?
Smaller.
If we're moving it that way?
Bigger.
Bigger. So if we're making the mantissa bigger, what do we have to do to the exponent?
Smaller.
There we go. So why don't you give it a try? Okay, so I've now written out the number. This bit in yellow is the mantissa. This bit in blue is the exponent. Now, there's something that's omitted between these first two numbers. What's omitted? Yeah, the point. In this case, it's a binary point, right? Because there you go. So there's a binary point that goes right here. And that means that the number begins with 0.0, thus indicating it is not
Normalized.
So what we're going to need to do is take this point and then move it so it goes once, twice over there. I'm going to rewrite my mantissa with that taken into account. So it would be 0.1101. Stop.
No, 3
Yeah, now I need to pad in because it's 7 long. I've only got 5. So 1, 2, buckle my shoe. No, that's right, isn't it? 7. 7, there you go. That's 7 things in there. 7 bits, binary bits for my mantissa. But of course, now that I've gone from this mantissa to this mantissa, I'll have to change the exponent to be able to take that into account. Moving this point to the right, is that making the mantissa larger or smaller?
Smaller. Larger.
Now, here's the tip I'd always come back to. I'm going to do it again. 1.76, yes? I move the 0.2 to the right, so I move that once, twice, thus giving me 176. What's the effect of moving the point to the right?
Bigger.
Making it bigger. And those things are consistent. So when I moved it to the right on binary, same deals. The Matissa has become bigger. Therefore, the exponent has to become smaller. And here, if you can figure out what the value is, you can see that actually this number is last column, because it's 2's complement would be, and so therefore minus 16 plus 4 minus 12. Yes? No, sorry. There's no minus 16. It's 5 originally, quite right. And because it's 5, I've moved it 2 to the right. The exponent, the Matisse has become larger. The exponent has to become smaller. So the exponent is now 3. So 3 would just be 0, 0, 0, 1, 1. And there, thus I have now normalized that number. Good question. Always assume it's in 2's complement. If the mantissa wasn't in 2's complement, what would it stop you being able to do? Yeah, you'd never be able to represent a negative number. If the exponent wasn't in 2's complement, what effect would that have?
You would get a number smaller than 1.
Yeah. So, because when the exponent becomes large, it allows you to make very big numbers, positively large. If you make it very negative, it allows you to make very small numbers. So, assume that both will be in 2's complement, even if not stated, albeit it should be stated. Remember, these are exam questions, so what you're looking at here is what you'd get. So, here, that's how it's stored inside the computer, and there are 2 things omitted. One is it didn't do the point, that went there. But also, if I was to actually, so 1.76 times by 10 to the power 3, yes? Which would become that number. It's very similar in terms of binary. In fact, it's identical. So in this case, this original number here, what you could actually write it out as is 0.001101 times by, because it's binary 2, and then to the power 00101. But what happens inside the computer is the point is always registered as being between the first 2 numbers. So therefore you can omit it. And because it's always in binary anyway, you can omit the times 2. So essentially they take that bit, and it's there, and they take the exponent, and it's there. Cool? All right, Good question. Have I actually answered the question fully? I suppose what I should do is put it into this original form. So probably what I should do is actually just write out is R equals 0, 1, 1, 0, 1, 0, 0, and then 0, 0, 0, 1, 1. But when you do it, don't make your zeros look like 6s or backwards 6s or something, right? Like, do it good. Good. 1 second. Like I did. Perfectly. Right. So in this question, it's a different tweak on a floating point question. Now, it's saying that you've got the first 5 bits are the mantissa, the last 3 bits of the exponent. Convert it to denary, so to convert it to base 10. Okay? Yeah. Give it a try. I've looked at this first question. Bit in the yellow again is the... Why have I made this? Why have I only picked up the first 5 from here? Indeed. So make sure you read the things, okay? So it isn't... Okay, fine. 3-bit is the exponent. What is omitted? We talked about what's omitted between the first 2 numbers. The point. Now, what I'm going to do to turn it back into fixed point is I need to roll this back down to 0. So this is 3. I'm making the exponent smaller by 3. If that's smaller, what becomes the mantissa? Bigger. So which way do I go to make it bigger? This is a suggestion. How many times do I go to the right?
3 times.
So it's once, twice, 3 times. I'm going to rewrite the number. So it's 110.0. And then if I'm looking at the numbers, on this side it's a half. 1, 2. You might be tempted to write -4 here. Don't do that because it's a positive number. Technically, the -8's there because it's 0, -8. Yo?
But you want to keep the 0 there, so it's 5 bits.
Well, I'm converting to denary, aren't I? So, yeah, I could but because I'm not trying to re-put it into a normalized form or anything, in this case it doesn't really matter. So the value is, what's the value?
6.
6. And then for the other one, what kind of a number is it going to be?
Negative.
So maybe with a negative one, it's going to make sense. 1 second. Let's attempt the other one. Spoiler, but the fact that it starts with 1, 0 indicates it's what kind of a number? Negative. So we'll have to bear that in mind. Don't consume the negative number and suddenly turn it into a positive. That means we've gone a really... Okay, great. So I'm looking at this number now, and it's pushing us in both directions. Now the exponent is actually negative. So in this case, we're going to take this negative 1 and to put it into fixed point. What do we need to do? What do you need to make it, so basically to put it into fixed points to make that back to 0. So what are you going to need to do? Add 1, yeah? If we make the exponent larger, what we have to do with the mantissa? So we went right, made it smaller, so now we need to go left. So in this case, we've got 1, so the dot was there, yes? So we've gone 1 to the right, so it's like 1.101.
Should be 0.101.
That's right, exactly, yeah. You have to, and it's worth bearing in mind. But now we see the logic. It's good that we're doing this today, isn't it? If you don't pad with the 1, you're going to convert it into a, which is not ideal. So I made the exponent 0, so therefore the exponents become larger. As a result, I need to make this smaller, the mantissa. If I go to the right, I make the mantissa larger, so I need to go to the left to make it smaller. So that's 1.110. So what I've got here is I've got negative 1 plus a half, negative a half, plus an eighth. So the answer would be negative, well, let me do it, there we go, negative 3/8, which in this case would be negative 0. It's 0.25 plus, so 375. Yeah. Now, it's really worth talking through what Charlie did, because it gives you an alternative route, especially if you're like, Jesus, I don't know if I'm going the right way or not, because you can actually check your answer. So what he did is he looked at this original number up here and here, and so that actually, if you look at it, is, so because we've got minus a half plus a quarter, we've actually got the value negative 3/4 times by 2 to the power minus 1, which is half. So 2 to the negative 1 is 1 over 2 to the power 1, which is a half. Minus 3/4 times by a half would be negative 3/8. I don't know whether that's easier. Now I've gone through this. I don't know if that is making it easier for you or not.
Say minus it from the 1.
Well, if it was different
Like,
numbers.
how can you get minus 3/4?
If you look here, that 1 represents negative 1,
Oh, and then you're adding whole numbers.
and then you're adding a quarter to that.
You're adding positive.
So minus a half plus a quarter is
3/4?
minus 3/4. Yeah? And then you times it by 2 to the negative 1.
No, okay, alright.
Yeah, 2 to the negative 1 just means that you go 1 over 2 to the power 1, which is a half. Negative 3/4 times by a half, minus 3/8, which is here. I don't know, like, I honestly, it depends, because some people, it's then going to create a labyrinth in your mind where you get confused and you can't pick any option. So if it works for you, it works for you. If you saw the way we discussed it, yes, putting it to a fixed point and converting it, does it work? Yeah. So I'm tempted to say you can just be consistent with that method and you will get the right answer as long as you don't make a mistake.
Can we bake a cake?
No. So guys, now it's going to flip it the other way around. You've been given the denary value of positive 3.5, normalized binary number, so floating point number, 5-bit mantissa, 3-bit exponent. Would we use 2's complement?
Yeah.
Yes. We don't need to use it actually for positive 3.5 because it's a positive number and a larger number, but... Okay guys, so let's talk about how we're going to convert a denary number like this into floating point. So first of all, what we...
Normalized binary.
Yes, normalized floating point. Thank you. Now, we need to put positive 3.5 into fixed point. And so we'll go along here. Now, this is, I've just picked this by example. Clearly, if there was a smaller number on this side, if it was like 0.00025, I'd need more fractions on this side. In fact, I only need to go up to a half, truthfully, for this bit. And I put a negative bit in there, but do I need to use a negative?
No.
No. But I've put it in there, and I think it's a good habit to get into, simply because what could happen is that you do need to represent a negative number, and you forget to stick it in there, and then you're going to look like a bit of a wally when you're like, oh, I've just turned it to positive. I've turned water into wine, or something. And so, let's go through in here. Indeed, it's the spirit of something. Positive 3.5, so no negative 8s, and then is on you, Mops. What do you do?
0, 1, 1, 1, 0.
And so now I'm holding the number, but I'm holding it in fixed point. So what I want to do is put it into normalized floating point. And the question will be, why is that not normalized? Because to be normalized, it needs to start with what? We've been discussing it today.
0,
Point.
1,
If it's,
positive.
and is it positive?
Yeah.
So I'm going to demonstrate that this will then come along once, twice. That'll work for me, won't it? Not want it? Yeah.
Yeah.
So I'm going to write down the new number. It'll be 0.111. Do I stop?
No,
Never.
When do I stop?
after 1, 2, 3,
So 0, 0, yes?
4. No.
No?
1 more?
0,
Here.
yeah? Now, remember, you have to put it into the format described. So what's the format? It says,
Yes, you need to add 1 over 16 in the last time.
so it's a 5-bit mantissa.
Yeah.
The bit I'm making right now is the mantissa bit. So how many bits am I using?
Okay, you're making it.
So how many bits am I used?
1, 2, 3, 4, 5, 6,
7.
7.
So what should I do now?
Remove 2 of them.
There we go. From which side? Right or left?
Left. No, right.
Yes. Okay. Now, remember this. By moving the arrow 2 to the left, have I made that number smaller or bigger?
Small.
Big BB.
No, but going from here, I've made it smaller, quite right. So I then need to make the exponent
Bigger.
bigger. By how much?
1,
2.
2,
Yeah? And then how many bits for the exponent?
3.
So what I'm going to do is the exponent.
Add 2.
Yeah, 2. So if I'm doing that, remember the exponent's also going to be in 2's complement. So it'll be -4, 2, and 1. So it will be
0, 1, 0.
0, 1, 0. And if I want to do at the end, to put it into sort of a nice form for people to see, I could say 0, 1, 1, 1, 0, 0, 1, 0. Couldn't I?
I will not solve it.
Yeah, and I go, no, that's it. Good.
Yes.
Let's discuss the strategy we're going to use.
Like, we will add 1, something like that.
We've got 2 floating point numbers.
Yeah, I got it. We will add them first.
To do negative,
You should add 1.
you could say this plus the negative version of that.
Yeah.
Bear in mind, though, these are the things where you could go wrong. These are not, they've got different exponents.
So you make the exponent 0, put it into fixed point, and add
Yeah.
it in fixed point.
So I would say that the safer way is to convert both of these to fixed point, yes, and then make that one negative, add it, and then renormalize. Alternatively, as long as the exponents are the same, so if as long as they were 0, 1, 1 or 0, 1, 0, they're identical, it would also work. But I think it's safer just to go to fixed point. So if I'm in your shoes, and I'm not, but if I were, I'd get the fixed point for both of those numbers, yes, boom, boom, can get the negative for that one, then add the two numbers together, then renormalize. There's quite a lot to this question, isn't there? But best of luck. So stage number 1 is me putting these two numbers into fixed point, and we'll do that now. Okay, great. So now what I've done is I've taken these two values that were normalized, I've put them into fixed point. And what we're saying, this second number here, we need to make it what? What do we need to make that second number? Negative. The danger, here's the danger, is that, look at the columns, that's units of 1, 2, 4, half, a quarter, an eighth, a 16th, and a 32nd or 32th, I don't know, whatever, 1 over 32. Now, if I flip this, and I'm not careful, I'm going to end up having that be negative 4. So if I put 0 here, to turn it into negative, I'll flip it, yes? And then I will plus 1. So if I flip it, I make that 1, 0, 1, dot, 1, 0, 1, 0, 1. If I add 1 to it, it's going to be 1, 0, 1, dot, 1, 0, 1, 0, 1, 1. Yeah, that's right. 0. Now, what does that 1 represent to me? Well, it should represent negative 4. But you see that column there? It's not. So this negative number I've tried to make, is it negative? No, it's positive. Now, if I just change that 4 to negative 4, will that fix my problems? There's a real question here, guys. I want you to think about it. If I change that 4 there to negative 4, that will make that number negative, correct? What about this number here, the top number? What would that make that number? This is the question. So that's not negative right now. If I change that to minus 4, does that fix my problem, Zakhtar? If I put that as minus 4, would that make that number negative? The answer is yes. Yeah, it will do. And what about this number?
It will be also.
It will be negative.
No, is that what I want to do?
No.
I want to retain this being positive, but allow this to be negative. Here's what you'll need to do to fix it. This will generally happen. I need to add in another column, negative 8. And I've told you this before, I remember a while ago. If you pad with a 1, actually it doesn't change the value of it, but it does allow me to have those two values like that. So now that allows me, and so here, sorry, for the top one, it'd be 0 here. That now allows me to have those two values. So now this value here is a positive value, and that's my negative representation. So now I'm going to write those two out next to each other. This is worth bearing in mind. This number here, which one's a bigger number, this number or this number? The one on the left or the one on the right?
The one on the
Left, because it's times 2 to the power 3, that's 2 to the 2. So being as that this is the bigger number and you're taking away the smaller number, what do you think the number will, and that's the positive, it's going to stay as positive. So this 1 at the end, you'd anticipate will have to get pushed off the edge for it to make sense. And so let's explore that. 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2. What do we do about that? 0, 1, 1, 0, carry the 1, 0, 0, 1, 1, 1 and 1 is 0, carry the 1, 0. And see, that would normally be an overflow, but in this case, what's it changed about the value? It's changed it from what to what?
positive to negative.
Well, in this case, negative to positive, in fact, isn't it? Because it was, yeah. And so this value here is 10.0111, and now I need to, is it normalized? So how do I fix that? Why is it not normalized?
You would.
It's not
Yeah.
1.0. It's not 0.
And this is the point where it's actually important that you've paid attention as to whether you think it's positive or negative, right? Because if I thought it was negative, I could just move that by 1 and say it's 1.0 something. But is it negative? So because it's positive, we will go there, and I'll rewrite it as 0.100111. How many?
1, 0.
See in here, we've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So what will I need to do? Pad with a 0. And what's my exponent?
0, 0, 1.
Yeah. Because what's happened is because I've gone twice to the left. What have I done with Mantisa? I've made it bigger or smaller? Smaller. So the exponent will be positive 2 or negative 2. So 0, 0, 1, 0. Okay, guys. So this is a bit more of a without style. I apologize. The style's gone now. We're adding these three together. There's no negatives to worry about. What's the strategy we're going to adopt? Turn them all into fixed point. Some of it's going to be a little bit funky because that's 4 and that's 6 and that's 3. So the point is going to be all over the place. But that's probably worth doing because then we can figure out how we need to pad it to make it consistent. You could add all three numbers simultaneously, but that is harder to track because remember, you could get a 4, you get a 1 and a 1 and a 1 and a carry 1, and then you have to carry it twice over. Or you could just add 2 and then to get the result and add 1 to that. So it's up to you. I might, do you know what? Because I've never shown you properly how to add 3 together at the same time, and we've only got 5 minutes, I'm going to do it that way, but I'll give it a chance. Best of luck. This will not present a difficulty with me. I have now converted all of these values in floating point to this, and these are all, what are these things? These are fixed point, and now I'm going to bigger it.
The ones that hang off the edge.
So 0 and 0 and 0 would be 0, 0, 1 and 1 is 2, carry the 1, 1, 1, 0, carry the 1, 0, carry the 1, that would be 4, so that's 0 here and 1 over here. That's 2, 0, be another 1 there. So that's 2, 0, carry the 1, 0, carry the 1, 0, carry the 1, 1. And then 0 at the end.
Oh, look, I got it wrong.
And then you need to just, oh, that's the worst zeros in the world. And then that's going to have to, because that's here, you have to go once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. Yes?
Oh, look, I got it
Is that what you got?
No,
I stopped with that. We got it wrong, bro.
Genuinely, that was a stupid question. I shouldn't have done. You won't get something this stupid. This is what happens at Christmas.
You know
What would you normally have genuinely in the future? So let me give you some feedback about what you would normally get.
Mr. Foster,
It's here.
the council has decided.
Yes,
You have small PP.
that is recorded. What you normally get is you get. So for instance, you get 2 to the power 3, 2 to the power 6, and 2 to the power 4. What is much more likely to happen is you get 2 to the power 4, to the power 3, and maybe to the power 4 again. It's what's caused the problem is that to the power 6 and the power 3 creates this huge spread, which has then created this monstrosity here.